Good afternoon on this lovely sunny Sunday, and welcome back to my workbench, where for the third time I've got this Damned Dell power supply open for some work. And if anyone's seen the previous video about this, you'll see where after a bunch of mucking around I did on the secondary side to fix a bunch of corroded parts in the output monitoring board and all that, the primary side went bang after about a minute of testing, which wasn't very impressive to me. Quite annoying. Anyway, fortunately, all was not lost. I had thought initially that the main switching FET had blown up, as you do, but fortunately it hadn't. The actual main power supply seemed okay. What was actually the problem, this little chip here which runs the 5-volt standby rail. Now this is a Power Integrations TNY266. It's got a little MOSFET and switching circuitry built into the same chip. It's a little highly integrated little device, and that drives this transformer here, the small transformer there, and that does the 5-volt standby rail. And it's this one that went bang. It took me a while to find it because the thing had actually blown out the side. There's no hole on the top, nothing on the bottom. It's a very small amount of damage just on one side by one of the pins, the drain pin for the internal MOSFET actually. You can see in this picture here where I've shown where it's sort of split out along the side, but yeah, not very obvious, and that does happen a lot with components like this. They can blow out the side or underneath, or somewhere where you don't often see the damage. So when you're visually inspecting a board for blown components, you sometimes have to sort of take a guess at what might be bad and have a good look around and the sort of usual suspects. And it makes sense, this kind of thing will blow up. I've actually seen these kind of chips explode a few times before. They seem to be good at doing it. I'm not entirely sure why. I think my guess is probably the integration of a high voltage MOSFET into such a small package, along with a bunch of other circuitry. I don't know. I think the high voltage, continual stress, these things running probably quite hot as well, and just that kind of thing. I think they kind of try to pack too much stuff into the really small little package. So yeah, I don't know. I don't like these things that much. I mean, they're convenient, I guess, for circuit designers, but in terms of reliability, I kind of like to see a separate MOSFET and a driver IC for that. But hey, it's cheap, it does the job, and yeah, this power supply is pretty old, so I guess, in terms of design life and all that and whatever, it's not too bad. But yeah, anyway, I've seen quite a few of these blow up now, so I'm not that impressed with them. And not just this particular model either, but other switching, little integrated switching ICs like that too. But anyway, that's irrelevant. But anyway, so once I discovered that was blown, I thought, well, okay, that's not too bad. I had a look online and I found Mouser still had them. I think the particular one might be obsolete. I believe the TNY276 is probably the replacement for it. The Tiny Switcher 3 series. Probably would have worked if I'd bought one of those, but yeah, kind of a bit better with something like this. It's best to go for the original part number. So I bought a bunch of TNY266s from Mouser. Pretty cheap. I think they're about $1.80 each or something. So have a few spare and not too bad. So I figure it's cheap enough. Nothing else really seemed damaged on this power supply, so I'm hoping I can just put a new one of these in and it should work. That's my plan anyway. And if that doesn't work, then I guess I really will say, well, forget about the whole thing. But for now, let's try that. So anyway, I got this the main switching MOSFET on its heatsink. I had to take that out to discover that this was blown, because that's kind of hides underneath the heatsink. I just put that in an anti-static bag so the MOSFET doesn't get damaged. And I'm also going to use also need a resistor, so the current sense resistor for this chip. That also got blown out, obviously, when the thing died. So it looks like what's actually happened with this chip is the internal MOSFET is shorted from drain to source, and of course this current sense resistor is obviously from source to ground, so it's seen the full mains voltage, rectified mains voltage, 300 volts across it, and that's blown up, so I'm going to have to replace that as well. In terms of what caused this to explode, well, not entirely certain at this point in time. I would say it's just old age on this part's part. There is some glue around it, but it's not the evil conductive glue that they used on the output side. It's some pretty decent, nice white glue that, as far as I can tell, shouldn't be an issue. But yeah, I think it explains the problem I was seeing with this power supply before, which was it would turn on, it would turn off, it would randomly power up and power down. And I think what was happening was that the 5-volt standby rail, which gives power to the secondary side, supplying power to this management IC, monitoring IC that does all the power up and power down and stuff. So I think what was happening was this IC was failing. Sometimes it would run, sometimes it wouldn't. And I think, the secondary side wasn't getting any power. Without any power to that, there was no power to feed back to the power up and power up opto isolator, which sends the control signal to the main switcher. So I think what was happening was the whole supply was just shutting down because the 5-volt standby rail was coming on and off. Possibly the control circuitry inside this chip was failing, and eventually it just failed to a point where the internal MOSFET was turned fully on, and it just blew up, because obviously you can't do that, it has to be switching on and off for anything. But anyway, regardless of what that, so the other problem which it could have been is the snubber network, and that is I'm not sure about the failure rate of that, but with a transformer or any other inductive load, if you're switching that, if people know about inductive loads, every time power is removed from an inductive load, there will be a reverse voltage spike generated by the inductor or transformer or whatever itself when that happens. And especially in this, with high frequency, high voltage, you need some diodes and capacitors, resistors basically across that coil winding, so that any high voltage pulses are basically filtered out by that network. And generally you have a diode in parallel with a resistor and capacitor, and that's a very common, typical thing for these switch mode power supplies. This one has two back-to-back diodes, and then they've got the capacitor. So not exactly the same as the datasheet sort of default thing, but still a pretty typical arrangement. And I've checked both the diodes. They, typically what you'd see, maybe the diode will go open circuit. If the diode goes open circuit, obviously it can't conduct the spikes. If the capacitor goes open circuit, same problem. The resistor also could go open circuit, and again, basically, typically I think what happens is one or all of those components go open circuit, and they can't filter out those spikes. The spikes feed back into the switching transistor, and if they exceed its maximum voltage rating, then it can be damaged. Also, the spikes can also go out through the output and cause problems with noise on the output as well, and possibly damage to the rectifier diodes in extreme cases. But I don't think that's what has happened here. The diodes seem okay. The resistors all check out fine, apart from the current sense resistor, which has got a hole blown in the side of it. I haven't actually taken that out yet, but I just had a look at that before, and it's dead, which is not surprising. When your main MOSFET shorts, the current sense resistors usually get blown up as well. Pretty common thing. So if you do have a blown MOSFET or a blown switching IC integrated like this, check the current sense resistor. If there is one, very likely it'll be blown as well. Another common thing that can happen is any feedback opto isolator or control opto isolator can also be damaged on the transistor side, usually going open circuit or short circuit. Not as common as, say, the current sense resistor blowing up, but if the whole entire circuitry inside this chip has basically turned into a lump of metal, then 300 volts could have gone into the opto isolator, which is only really rated for about 20 volts or something. Certainly not 300 anyway, and you can get problems there. So yeah, anyway, but everything else seems to check out fine. I'm going to take this capacitor out and give it a test, because I can't test it in circuit. So I'll take that out. I'll take out the dead resistor. I'll test the capacitor, make sure hasn't gone open circuit, make sure the value is still correct, and replace that resistor, replace the IC, and everything should be working again. At least that's the idea. I don't think the fuse blew, fortunately, because it's all tucked away behind all these wires and inside heat shrink, and would be quite annoying to replace, but I've done some tests on that, and continuity tests on that, and it seems to be working fine. So looks like the IC blew up instead of the fuse. But yeah, so that's pretty much, I think, the detail of what's happened here, what I'm going to have to do to fix it, and after that, hopefully, the thing will actually be usable. Yeah, unless it blows up again, but I don't think so. I think I have, well, I have some confidence that this is finally going to be the last of the problems in this thing. Alright, so I've got my soldering iron fired up, and I'm just about to remove those two components I spoke about. First of all, the current sense resistor, which obviously is completely broken, and I want to take that capacitor out and give it a test just in case it's faulty, but it's probably not. I do honestly think that the IC is just blown up all by itself, basically. I've seen it happen before. So, let's see. Right, so that's the resistor, and I should be able to grab that. There we go. So that's a, I'll have to take a separate photo for this, but yeah, it's a little 1 ohm resistor, and it's got the bottom side completely burnt out of it. You'll see that in a second. It's quite amusing that those things fail like that, because they often don't blow out on the top side where you can actually see them from the board. They usually blow out on the bottom side between the component and the board, so it can often be quite tricky to discover that they're actually faulty. So yeah, but again, like I said, if you already know that current sense resistors are likely to blow up, and you've got a blown MOSFET or blown IC, then it's a good thing to check. First thing to look for. So that looks alright. So now I'll take out that capacitor and give that a test. But I mean, yeah, it's probably fine. And that's just a standard disc ceramic rated for 1000 volts. Okay, the body of that seems to have been slightly cracked. It's I'm not going to say falling apart, but it's had a bit of damage on the back there. I don't know if that's indicative of a problem or not, but that's cool. See if I have anything to replace it with. Whoops. I might have to replace it anyway, just because of the damage to it. It's not really a smart idea to leave something like that. Now, what is this? 103, so 10 nanofarad. Could replace it with one of these. 3 kilovolt part. Which is a bit ridiculous, but might be all I've got. I don't think I have a 1 kilovolt part in that value. I mean, this capacitor might be fine, but I am a bit worried about the fact that the thing is cracked around the lead there, and you know, moisture could get in and damage it in the future. So it's probably a better idea to just replace the whole thing with a brand new part. But I'll replace the resistor first because that's the hardest component to get to. When you're working on something like this and you've got a bunch of components all next to each other, it's best to put the shortest components in first, or the smallest, or the ones that are going to be close to a large one. Because otherwise you put the big ones in first, then it's much harder to fit the new small one in. So if I put that capacitor in first, I'd just be annoying myself with the trying to fit this resistor in down beside it. So if I can just grab that there. So I'll just put that in. Let's poke it in with the end of this. And we'll put this hilariously huge capacitor in the side there. And that should be all we need. Should be able to solder that in without too big of a deal. Alright then. That looks alright. And it's got this hilarious big blue capacitor in there, but hey, whatever. It's all good. I might just I might try and cut some of the glue away next to these IC pins, just in case, you know. Might help if I heat it up first, that often helps with this kind of stuff. Unless it's the kind of glue that dries with heat, that cures with heat, but as far as I can tell, most of these things, they usually they're quite softened by heat, and this one does seem to be softened by heat, so that looks good. Alright, so anyway, suppose I should open these as well. So I need one new IC, not three, hopefully not three anyway. There's a brand new chip there. Can put that in. Hopefully. Alright then, so that's that. We got the 3 new parts in. Current sense resistor, new IC, new snubber capacitor because, well, may not necessarily need it, but probably a good idea considering the crack in the side of it. Ah, of course, I have to put the main MOSFET back in. Oops. It's that's a good idea, isn't it? Then I wonder why none of the main rails went. Oh dear, I'm taking too fast here. Need to slow down a bit. Don't get too overexcited to test out the new thing and so yeah, as you can see, that heatsink goes over the top of everything. It's very hard to see anything while that's in there. So I had to take that and the MOSFET on it out before I could do any work on the thing or even look at what was going on. But that's not too bad. And that's quite a common thing with these kind of devices. You often do have to take out the heat sinks or some other large part to get at smaller ones underneath it or next to it. Kind of annoying, but hey, it's just how it is. At least with this one, the heatsink is quite small and there's only one transistor on it, so wasn't a it's not a big deal or anything. There we go. So, assuming that's all that was wrong with it, it should theoretically actually work this time. So just spreading the heatsink paste around on the inside of the case here, sort of needs to be smoothed out again so that it all makes sense. But yeah, unless like the transformer or something is damaged, unlikely, but you know, it happens sometimes. As long as nothing like that's happened, should be alright. So let's put it back together. Just tap this dust out of it. Brush the dust out maybe. Right, okay. Can remember which way around this goes. I think I maybe need to put the PFC coil in first, maybe. I think I have to screw that in first before I can get the other bits in. But I'm not 100% certain on that. Or was it the oh no, it's one of the screws for the main board is blocked by the coil, so you have to screw that in first before you put the coil in. Now it all makes sense. So hang on, now I need to get the screws. Alright, so now I've got the screws here. And I should be able to start putting it all back together. I'll just put 2 of them in for now. I don't think we need all of them at this point. Not for a quick test anyway. Goes there. I will put the screws to the PFC coil in though, because I don't want that flying around. Probably want the one for the heatsink. Which doesn't seem to want to go in. Am I using the wrong screw? Quite possibly. Maybe it's this one. How strange. Anyway. That's all back together, and despite the fact that it's covered in heatsink paste, just going to wipe that off. Shouldn't be too big of an issue with it. That does go in here approximately, as far as I know. Somewhere like that. There we go. So I'll just clean the rest of this off my hands, and I'll come back and we'll give it a test and see if it goes up in smoke again. Hopefully it will not. Hopefully this time it'll actually work properly. Alright, so I've got everything assembled on the bench here, all set up for a test, and hopefully we'll see what happens. Well, I'm sure we will see what happens, but hopefully what happens will be a good thing and not any more explosions. Right, so obviously I've got the power supply plugged in. I've got a multimeter over here which I can use to check the voltage rail, make sure it's okay. So mains comes into the power supply through this contraption over here, which is part of an old power supply case with a light bulb, series light bulb, and with the mains and the thing. And this goes out to my isolation transformer, which is under here, and then that goes down to the thing. So at the moment it's not actually plugged in to the wall. The transformer input is still hiding underneath here. This is the actual plug. I don't know if you can see that, but this is the plug for my transformer, for the isolation transformer. So at the moment nothing's connected whatsoever, but in a moment it will be connected. So the basic idea is that the light bulb in series with the line input to the power supply, or whatever it is you're testing, that will limit current under fault conditions. If you don't know, a light bulb actually increases resistance as it heats up. Now this obviously only works for incandescent filament bulbs. It doesn't work for LED bulbs or fluorescent bulbs. It only works with an incandescent one. Quite useful anyway. They're kind of like the inrush limiting thermistor that's in the power supply itself, but they operate in the opposite direction. So while the inrush limiter in the power supply starts off at a high resistance and drops down to a low resistance when it warms up, so that limits the inrush current to the capacitors when they're charging up, preventing like the power switch in the wall from arcing too much or anything like that, preventing high inrush currents. It settles down to a low resistance when it's hot and allows the circuitry to work normally. The light bulb on the other hand works in the opposite way. It starts out with a low resistance, so it'll allow current through, but as it heats up, as it warms up, the resistance increases and it actually draws less current, and it of course prevents more current from flowing through it. So if, for example, the primary side in this was shorted, it would try to draw as much current as it could, but with the light bulb in series with it, the amount of current that can flow is limited to a maximum by whatever the light bulb normally runs at. So basically the idea is that hopefully if you're testing something like this, you put the light bulb in series, the light bulb will limit the current if there is a short, or typically I think for power supplies, if the controller IC is faulty or not working properly and it just turns the main switching MOSFET on hard, which normally means it's just basically a dead short across the mains. and through the winding of the transformer. If some silly thing like that happened, then the bulb would limit the current and the transistor would hopefully not be blown up, and you'd be able to turn the thing off in time that it wouldn't immediately just explode. And of course that works for other things as well. Doesn't have to be the transformer, the transistor that might be shorted, it could be anything. But yeah, basically if you have a shorted problem, then it will limit the current, hopefully enough so you have enough time to turn it off before the new parts you've just put in get destroyed, and then you can troubleshoot further and see what's going on. So what should actually happen with this? When I plug it in, the bulb should briefly flash as the capacitors charge up, and then if it's operating normally, the bulb should probably just fall back down to a very low brightness, or maybe even completely, or seem completely off. We're passing so little current it won't actually light up, and therefore it won't be limiting the current because it will be at a low resistance when it's cold, or relatively cold. So here we go. Time for, well, hopefully time for a working power supply, and not time for a bunch of fireworks, but yeah. See what happens. 3, 2, 1. Woohoo! Well, nothing here has exploded, so that's a good start. So yeah, let's just move that over here a little bit, and let's see if the circuitry is actually running. So again, the fan's not spinning because the main power supply is not up, but if I check the purple wire, we should get 5 volts. We do, 4.995, which is pretty much exactly what we got last time. So at least there we go. The 5 volt rail is working. That new TNY266 is functioning. Everything's going okay from now. So there we go. I mean, it's obviously with no load, so we can't say necessarily that it's perfectly fine, but it does show us that, you know, transformer's okay. Shows the feedback's okay. Yeah, everything seems alright. Let's just leave it sitting here for a second, for a while. Let's just leave it sitting here for a bit, and hopefully nothing bad should happen. I could just sit here for another half an hour watching this, but that would be a bit of a waste of time. So what I'm going to do is actually do some tests. I'm just going to do that then. Or am I? Maybe I won't. Let's see what we got here then. Nope, there we go. Same deal. So, yeah. So it is running once more. So the whole power supply should be up this time. Obviously there's no load whatsoever, but I'll just run this as it is because this is where it blew up before. Okay, let's check all the voltage rails again. So 3.3 is fine, 5 is fine, negative 12 is fine, let's check 12, 11.7 again. I'm not sure why that is so low. 5 volts still 5. Power good is 5. So that's pretty much everything. I don't think there's no negative 5 volt on this, is there? No, it's a modern power supply, so no negative 5 volt rail. So all the rails are okay. Yeah, I mean the main 12 volt rail is a little low. I think that may just because there's no load. I mean all the other ones are in spec. Yeah, I mean, I don't know. I don't think that's a big deal. If the supply was running incorrectly, you'd see all the other rails would probably be low. The 5 volt and the 3.3 would be low as well, but probably it's just a low load condition. If I plug that into an actual computer, then the 12 volt should come up to normal voltage. But yeah, there we go. I mean, it's going. It's doing its thing. It's not exploding like last time, so that's a good start. Yeah. Who knows what the problem was? I think that IC, the switching IC, the TNY266, I think the old one was just probably worn out. That's my guess, really. And maybe that capacitor was bad, but yeah, I don't know. Probably just old age. Like I said, I've seen those little integrated power switch kind of devices blow up before for no apparent reason. So I don't know. I think it's just a downside of integrating the MOSFET and the control IC into one package, into a really small package as well. I don't know. Maybe some sort of thing to do with heat, high voltage, maybe electromigration, some sort of issue where the sort of electroplating happens inside the die of the IC, and the actual metal starts to sort of migrate and move with the high voltage and stuff like that, and I think it just causes failures eventually. So that could be what happened. I don't know. But again, yeah, like those things I mean, the hotter something runs, the higher the voltage, the more stress on it, the shorter its lifespan, basically. It's why the power MOSFETs and power ICs and stuff are usually the things that blow up. Some like little small transistor that switches the output on and off, that gets the PS on signal from the motherboard, something like that, pretty much will never fail because it only sees 5 volts and it probably only passes like 10 milliamps or less, something like that. So yeah, anyway, but that's good. Hopefully that solved the problem. So hopefully third time lucky with this thing. First time I had to replace all the blown output capacitors, and a few of the primary side ones didn't look that great either. Second time, the secondary side monitoring board and associated components were corroded by crappy glue, and replaced all that. And third time, replaced the 5 volt standby primary switching IC. Hopefully there won't have to be a fourth time. If there is, fourth time might just be the rubbish bin instead. But yeah, that's looks like, hopefully, fingers crossed, good result this time. Anyway, so yeah, let's give it some actual load testing and see how it goes. Okay then, so I've put the power supply back together, put the case on, made sure the airflow is alright, because obviously if we try to test this thing in open air it would probably overheat and blow up again. Something else would probably blow up. So yeah, so anyway, I had a look, everything seems okay, so I've plugged it back into the computer, to the dodgy dumpster Dell, and time to see if it actually works. So let's see what happens. Look at that. Okay, I'm going to need to plug my keyboard in, so let me just grab this. What have we got? I don't think my floppy drive is plugged in, but that's fine. What do we have here? that correct? That's not correct. I wonder if that battery's flat. It probably is, actually. Yeah, I think all these BIOS settings have been reset. Possibly this battery is flat. Let's just turn that off and see if there's a new battery. I think it might. So we'll look at this one. It's a bit crusty. Let's give it a test on this meter. Well, not a meter, but that's actually not too bad. A slow bright flash means that it's working. Like a brand new one, exactly the same. Okay, so maybe the battery's fine then. That's just me being silly. It's set up. Okay. Turn that off. Put that on there. Let's turn hyperthreading on. Turn that off. Security, we don't need that. Okay, so we want to change the time. What is it? September the 24th. 2017. The time is 5:51 p.m. Alright, so that looks good. Oh, yeah, Power Supply isn't blown up yet, and it's posting the system again now, so that's a good start. So let's see if this thing will actually run. Yeah, I think this system is a good candidate for running Windows XP, so I can access my EEPROM programmer and stuff. I had Ubuntu obviously pre-installed on it before, which I was doing some stuff with, but I don't really need that on there anymore because I've got this machine over here that has all my Linux on it and everything. So this one probably I'll just have Windows XP on it, because obviously I can't run Windows tools and stuff in this at the same time as I have anything else. So yeah. Yep. So there we go, everything seems to be working, and looks like maybe it was the 5-volt standby rail in the power supply that was actually the problem, rather than the corroded components on the secondary side board, although they were a problem, and I'm glad I replaced them now with new ones and cleaned all that glue off, because that could have definitely caused a problem in the future. It obviously would have been a matter of time before the legs on that transistor for the fan control and the voltage reference and all that corroded through, and obviously if the fan controller transistor fails, then the fan will not spin, everything else will overheat, and quite likely the primary side would have blown up completely, not just the 5-volt standby. So yeah, good thing I fixed that problem as well, but hopefully now the real problem of why this wasn't posting before and why the power supply when tested without a load would power up and power off and do weird things all by itself, looks like it was just that 5-volt standby rail was failing and thing just couldn't keep it together. So with a new IC, I think it's probably just the IC that was the problem, unless it was actually that capacitor. I mean, the diodes obviously they were fine, but I suppose I could test that capacitor, couldn't I? Let's see, how could I do that? Well, I could plug it just into this multimeter, couldn't I? So it's got a capacitance tester. It won't tell us if the breakdown voltage or anything is incorrect, but if I stick it into this thing, it should be, what was it, 10 nanofarad? Should be 10 nanofarad. I think I like to stick a couple of wires in here though to attach it onto, which is a little bit crusty, but hey. It'll work well enough to see if the thing's open circuit or not. So let's see. Seven, 8, 8.3 nanofarads, that's pretty close. That's what you'd expect. I mean, I am holding this with my finger and I've stuffed a bit of wire in the socket and it's not really that great, but I think it if I hold this thing on there at just the right angle, we can see, you know, 8.3, that's pretty good. I mean, it is a 20% part, I think, so that's well within tolerance. Probably this capacitor isn't faulty at all, there's probably nothing wrong with it. But yeah, like I said, the leg started cracking, and for a critical component with a high voltage rating, it's sort of, yeah, you don't really want to use something like that again, so let's put a brand new one in. And there we go. So yeah, I think really the problem was just that switching IC. I think it was just worn out and just blew up by itself. That's probably it. So anyway, hopefully this thing will be usable for a while to come. Yeah, because it'll be quite useful. It's a nice little machine. I mean, yeah, they're not that great in terms of cooling, obviously. They're quite compact and all that, but again, that is a benefit. I mean, you know, on a bench up here, you know, I want sort of as much space as possible, and a little machine like this is quite nice. And yeah, I mean, I'm not going to use it a huge amount. Just running Windows XP in that, so you know, not too worried about a shortened lifespan due to running hot, because I probably won't be using it that often. But yeah, it should work for now. That was a pretty easy fix. It's like a $2 worth of parts for the IC and a resistor and a capacitor. So yeah, well, there we go. It's pretty much it for this one, I guess. Hope you enjoyed that. Hope it was fun. Hopefully this thing is finally done. Hopefully that'll be the last in this video shenanigans with this particular power supply for now anyway. So yeah, all good. Good. Well, there we go. I'll see you next time.